Welcome to my channel. Welcome. I'm MC Toon. I hope you enjoyed that little intro. Today I've got a special real science talk with Almost a Doctor, who is joining me right now. Welcome, Almost a Doctor.
Well, thank you very much for having me on. I am keen to talk some real science because, as I saw someone mentioning in the chat, after listening to Flurfs for so long, you can't help but wonder if you've had a little bit of mental impairment. So hopefully today we can rest everybody at ease and hopefully stop the average IQ dropping too low.
Very nice. All right. Well, for anybody wondering, Almost a Doctor does have a YouTube channel. He obviously does a whole lot of other stuff in real life, but the YouTube channel's in the description. I've linked it in the live chat. And so please do go and subscribe. It'd be good if he were to get a handful of new subscribers from this. And I've watched a bunch of his videos and they're good. There's one in particular that's a groaner. You let me know when you find it. You send me a message. Which one is the groaner? No spoilers there.
But I mean, some of my early ones are pretty cringe.
No,
like the most popular one on my channel was the second I made. It's like I look back at that going, oh, I could have done a better job. But I guess if you can't do that, what's the point?
Yes. So, and I always tell people, don't worry, don't start your channel until you're really good at everything. Start and have them be bad and learn, and then you can leave them or delete them later as you feel you need. Anyway, why don't you let us know a little bit about what you do, what you're studying, and how it is that you are almost a doctor.
Well, yes, hence the name, as the name suggests. I'm currently doing a PhD and I'm a physicist. So I'm doing my PhD in spectroscopy, hence what we're talking about today. And I build gas detectors for environmental monitoring, but I've spent my undergrad and honors for anyone who's not really Australian or British is basically a one-year master's doing spectroscopy as well. So I've worked with making material for lasers in the past, and now I'm building gas detectors. So it's somewhat relevant. And I also do teaching and outreach and kind of science demonstration stuff on the side as well. And so the name Almost a Doctor actually came from one of Australia's top science communicators, Dr. Carl. I was spending the day with him because he was being very generous and giving me a tour of a radio station. And I suddenly found myself on the radio with him, and he called me Almost a Doctor, and I liked it so much that I was like, I'll take that as the handle. And well, PhDs, yeah, they're long enough. I don't need to worry about changing the name for a little bit longer. So yeah, that's my background. I actually deal with this. I basically play with lasers for a living, so no complaints.
Are any of these lasers on sharks?
Oh, you'll have to see my little video that covers that. People have told me they really like that one. We'll see, but yeah, no, I'm not going to comment on that. I don't wish to incriminate myself.
Well, all right. So you have some things you've prepared, some stuff to talk about. So why don't you move forward with that, and we'll all sit back and enjoy what you've got to share with us.
Yes, and hopefully I can teach everyone a little bit about spectroscopy and why you don't need a container for it. Sometimes you might want to use a container, but if you're dealing with astronomy, you definitely don't need one. So I have one of my old thumbnails, if we want to start with that, that's probably easiest. So this was off one of the early videos I made, and my goal today is hopefully to explain just enough about spectroscopy that everyone knows exactly what this means. So this is what Mercury looks like. So what do I mean by that? How do you get it? And what's all of the different colors? And then, as you can see on the little panel on the right there, what are all those stripes and where do they come from? Well, that's where we're going to go. Oh, yay, the laser pointer works. Okay, so spectroscopy, I said I'm going to basically show you how to do it, or at least some areas of it. I'm going to focus on absorption and emission spectroscopy. So that's the intro is just me. I'll cover a tiny bit of background of spectroscopy, who started it, where's it come from, and then I'll go into absorption emission, which is what mostly we'll use if we're going to look at stellar objects, including the sun. I'll show you my spectrometer. That's the one in the picture at the beginning. And then we'll go over Fraunhofer lines, which is basically how do we know what the sun's made of? So when a Flurf says they don't know we don't know what the sun is, or it's just a luminous body. No, we can do a lot better. And I'll show you how to do that. And then, of course, because who doesn't love a bit of James Webb at the moment, or as the science communicator who gave me my channel name says, the Just Wonderful Space Telescope. And how can we use something like that, plus some of the other stuff I do, to look for exoplanets and specifically life on them? So that's hopefully what we can get through. And if you're wondering, the picture in the background there is a laser cavity. You're looking inside a laser there. And as I said, I play with lasers for a living, and that's a photo I took myself. So if you want to know about wavelengths and how we know what ones they are, you can also build a laser, but I won't touch too much on them. So background is where we'll start, obviously. So most of you have probably seen something like this. The white light comes into the prism and it spreads and you get the rainbow color coming out. And that's actually the basis of spectroscopy, at least the ones that I'm going to cover. Every wavelength of light will refract or diffract at slightly differently, which is what gives you rainbows in the atmosphere. But it also means that you can split colors of light up. And on top of that, different elements will emit and absorb different colors. And so we can use this as a basis to basically tell a lot about the universe. If someone tells you we've got chemical X here, well, this is the start. But, well, who had the idea? Well, before we get to who had the idea, I do want to point out that I'm mainly going to be focusing on the visible part of the electromagnetic spectrum, and towards the end, we get to James Webb, obviously IR, but spectroscopy can cover pretty much all of the electromagnetic spectrum. Gamma rays, there actually are telescopes that do it, well, orbiting ones. One of the first times that they backed up a gravitational wave detection with actual optical detection, they also picked up the gamma ray burst coming off it. One of the, I remember going to a lecture by one of the professors at the university when they had that. So you can use pretty much everything, and radio waves in astronomy are also very, very useful. But again, I'm going to focus on UV, Vis, and IR, mainly because, well, otherwise, where would I stop? How many hours has anyone got? How many days has someone got if I want to start talking about them all? Because otherwise won't stop. Now, the person who generally gets credited with starting it is Isaac Newton. So back when he was doing all of his work with light, he was the sort of one who really went into this. Most of you are familiar with an image like this where he splits the light. But Isaac Newton, on top of just doing that, noticing that that you get the rainbow out, he did, I think, mention some of the dark lines that he saw in using the sun, because he often used flames, the sun, and various other light sources, but mainly fire and the sun to get his light for these kind of images that you make, because they technically are an image, which I'll cover when I show my setup a bit later. But he was a weird guy. I mean, at one point he actually used a series of mirrors to stare at the sun and sent himself blind for a few days. He had to go hide in a dark room, and then also found out that if you push on your eye, the actual eyeball in certain parts, you can trigger the flashes. So he got metal rods, like needles, and you can see the diagrams in his book. I'm not going to show any pictures for it. And decided to stick them in his eye and push. But Huygens, who came after him, was one who noticed that different colors diffract or refract differently. This is what I was getting to. This is why you get these ones. And then you come along, Joseph Fraunhofer. Those are the Fraunhofer lines. He noticed that there were dark bands in the light coming from the sun. There was colors missing. And that was when they started to go into, maybe we can actually use this. We can actually do something with this. Maybe those dark bands they're not random. They actually mean something, and they really do. Some of the earliest spectrometers were as simple as this. Flame, you have a prism just like I showed, and then you have some way of viewing it. This is fairly simple, but you could generally tell the difference between certain basic elements, but I'll leave off how for the next bit. So I do want to cover one more thing before I get to individual elements, and that's black body radiation, because if you're looking at stellar objects, you also need to, I guess, have a solid understanding of what that is. And basically everything emits a black body spectrum. It emits black body radiation. Now, black body in science is a very idealized model of what's going on. It's something that is in perfect thermal equilibrium with the environment, which most things aren't. But like most things in science, you start with a basic description and you go from there. You start with something general and then you can get more specific. And in this case, you can actually make a very, very accurate model, even if things don't fit with it perfectly. It's like maths. Maths is a tool with which we can use to describe reality. Well, this is another tool that comes out of the maths. But if you want evidence for the fact that it works, you're looking at it. When everything emits pretty much most wavelengths of radiation, but the hotter it gets, the more light it emits, and the bluer the color. So most of it's in the infrared. So like you and I, if we're looking in the thermal infrared, we can't see that with our eyes. We need a camera. Some animals can see it. But if you heat things up, eventually we can see it. So hot metal is the go-to. Certain, if you put even metal in a Bunsen burner, you can heat it up enough to do it. Same thing for fireworks too. The reason, but they're doing something slightly different. There's a few things going on there. But I do want to cover some numbers. And of course, if the math scares you, don't worry. I'm not going to get too busy in it. I'm just going to talk about what it means. The first one, the Planck relation is equals HF. That just says for every frequency or wavelength of light, you have an associated energy. And it's quantized. That was what Planck did. And he's actually a really good example of a scientist who was really good at science, even though he had personal convictions against the work he was doing. He didn't actually believe this equation was correct. He didn't believe in quantum mechanics. He believed in classical, but he's like, but the maths works. And if the maths didn't work, we'd end up with a problem where you'd end up with infinite energy scenarios, which you just can't do. But he's like, here, this makes the maths work. And then he derived the Planck function. If you're wondering what that weird bunch of maths looks like, that's just the graph on the right-hand side. All it is that for a given temperature, the other variables too, we've got, actually the other terms there are generally fixed. So C, speed of light, H, Planck's constant from above. But when you map them out for different temperatures, which is capital T, you can see that not only do you get more radiation coming off, more intense light, but it also, the peak goes bluer and bluer. And that's exactly what we saw earlier with the picture of basically the metal heating up. And this goes for stellar objects. So kind of an advanced warning. This is where we'll get to with the sun. But yeah, Planck did all this maths, but he didn't believe it. It was Einstein who came around and said, no, it's not just the maths. This is actually what's going on. And well, experimentally, it was all verified quite easily. And so they went on with that. And okay. But what it is really useful for is that when you look at a spectrum, you can fit it and get the temperature out. Or if you know what the temperature is, you can go back and get the spectra. So the two takeaways: one, you can tell the temperature, and you can tell where the peak wavelength will come from, which is this thing. B is just a constant that incorporates a number of those variables. D's the temperature. Oh, by the way, if you're wondering, sorry, that should be a point there, not a slash. But it's 9.9 micrometers, which is far out from what we can see. We're about 700 nanometers, so we're more than an order of magnitude. Well, so no, 3 orders of magnitude more than. No, 1 order of magnitude more than what we can see with the human eye for room temperature. So the maths works out. We shouldn't see it, but when you heat something up to even a few thousand, like you get in a blast furnace, you'll see it, and we do. But again, I don't want to spend too much time on the maths unless people have questions. But what it does give us is this picture, and I'll be coming back to it later, but this is why I spend all that time, is that the sun is hot. So it's got a very, very obvious black body spectrum, and that is where most of the light comes from. It comes from that energy that you're releasing because it's more or less in thermal equilibrium. Now, you'll notice that the solar spectrum in yellow doesn't quite match up with it, and that's, as I said, the black body is an idealized scenario, but when you take into account that there are a few other things going on, then it actually fits pretty damn well, and it gives us a temperature. And you'll notice that, especially for longer wavelengths, it fits really, really nicely. Also, interestingly enough, about 500, just above 500 is where it peaks. That's actually in the green. So technically, if anything, just in terms of, how much light is coming out, or number of photons, the sun is green. But you can't really say most of the energy comes from the green part of the spectrum, because that's not technically true. But you get more green light than any other. Most of the energy is still in the infrared, hence the sun is hot, but that's also because the infrared is a fairly big region. And what I'll get to is how we know this other red one, but we'll come back to that. But so far, the maths and what we see is perfect, but I know a lot of flat earthers will be like, no, but you have to do it yourself. So to do that, I do need to discuss absorption and emission, and then we'll get into me actually doing it. So this is just going to play. Come on. Yes. So this is what I had at the beginning. So this is one that I have playing. You can just see it. You simply turn a lamp on, and if you've got the rest correctly, you'll see it. Now, what you're looking at here is a mercury lamp. So you're just electrically pumping mercury. You're pumping a lot of energy in, and that energy, obviously, some of it comes out in the form of light. But unlike a black body spectrum, which is more or less continuous, if it's really hot, you'll see kind of a rainbow color when you do this, hence the picture at the beginning. You also see that you get distinct bands. So you get lines that come out rather than those straight lines, and that comes from something else that's going on. Molecules, when you're talking about electrons, and if we're in the visible region, this is what we end up moving around, they have energy levels. And like anything, if you're not pumping energy in, everything wants to go what's known as the ground state, the lowest energy state. And a good analogy is water running downhill. If you just let, dump a bunch of water at the top of a mountain, it will run to the bottom. And if you want to get it back up, you have to have a pump or some system or put energy in to move it. And same with atoms. And I've just got a very simplified two-level system. If the energy of the light, also HF can be written as H nu. That's nu and not V.
It does look like a V.
It does. And that got me for a lot, but I got told off by some of my professors. No. You want to write nu when you're doing it. And since this, okay, I'm going to listen to them. It's the same thing. It's just frequency. So you're putting the same numbers in. It's just how you represent it. We can play around with that. So if anything, just so no one's confused. So all this is saying is that when the energy of that light coming in that photon matches the energy difference, you'll get absorption. You'll move between them. And if that relaxes and that electron comes back down, you'll get that photon coming back out. And they'll be the same color if we're talking about more or less the exact same color if we're talking about elemental absorption emission. If you want to get into molecules, again, how many hours do you want and how many of these ladder diagrams do you want?
It gets more complex.
Yeah, that's it. To say it gets more complex is almost an understatement. Even I don't fully understand it. And this is what my honors was in. And I still deal with this. But mostly at the moment, I'm lucky. I just pick one transition I'm after and I go looking for it. But the main takeaway is that, you can put, and if the light matches the energy gap, it's like climbing a ladder. You can't step halfway between a rung. You have to step on the rungs. So you need the energy to be perfect. Then that light will go missing. And if you have enough energy there, then you can get the light coming out at the same wavelength. Now, you can make this go up also using thermal energy and electrical energy, which is actually the two main ways you power a laser, if anyone's interested. You can optically pump it. So you can actually run a laser using another laser, which is how a lot of people do it in research. I've done that, but you won't tend to find that for a laser pointer because that's pretty pointless. But anyway, some people also are familiar with this diagram. I just threw it in because it's the same thing. I just want to show that there are more energy levels. The other one was just a nice simplified version. But main takeaway is that you get the colors associated with those energy gaps.
And that's a bit simplified picture of the electron orbit.
Yes, I'm trying to balance here, not getting too bogged down in details.
That's a fine way to think of it, right?
Yeah, But the result is also really, really cool. What it means is that because all the atoms out, or the elements out there, have different electrical structures, different number of electrons to protons, and even then some of the ions will be different from their neutral counterparts. The ion is just you've put a charge on it. So generally speaking, in what we'll see today, it's when you pull an electron off, then you'll have a unique ladder. You'll have a unique energy structure that means that you get unique emission lines. And of course, if I reverse this round and I put the light back in, I'll see those as dark bands in absorption. And so we can see here the different, some of the different lines against a kind of a continuous background. Interesting enough, if you're looking at if you want a good evidence that this works, have a look at a fireworks display, which I think was, yeah, you can also do lamps out of it and get the different colors, and it's multiple wavelengths, which is why they're interesting colors. But yeah, so this is over my hometown because we have one of the biggest firework displays in the world. I think we have the biggest New Year's Eve fireworks display pretty consistently. So yeah, if you want to see some good things go bang, well, you know where to be on the end of December. So, but the different colors there come from the fact that they load the fireworks with different elements. When the firework detonates, well, there's a lot of energy in that, and some of that energy goes to heat, and that drives the emission, because you pump the electrons up and then they relax, and you see that coming out as all the pretty colors. Generally, if you see bright red in the fireworks, that's a good indication you've got strontium. And of course, you can start mixing color. My guess is the green flecks I can see in there probably coming from could be barium or calcium. Again, if I wanted to tell exactly what they are, I can run them through a spectrometer, which is the next part. But again, yeah, if you want a good example of how this works, fireworks, lamps. If you want a good test for black body spectrum, how they work, just turn on an old incandescent bulb, because that's how they work. It's also why they feel really warm, because they have to get quite hot, and you're losing a lot of energy to infrared. So they're not the most efficient way to light something, which is why LEDs and fluorescents are much better. And the fluorescents are doing something somewhat similar to emission, but yeah, it gets complicated. But if you watch, I do have a video on my channel where I basically go through and show you the spectrometer as well in a few minutes. And one of the things I do is I pointed at the fluorescent lights in the lab, and you can actually match some of the mercury peaks up. Yeah. Because they do add traces of mercury to the fluorescent bulbs, because it helps give the color. And so yeah, you can show that when they say there's mercury in there, they're not lying. But they are pretty efficient. Anyway, quick summary. What you want to look at is if you've got a continuous spectrum, so say a black body, then you'll have something that looks like the top one, nice rainbow. We've all seen rainbows before. Absorption, you actually generally have to put a background there. So you can either take one wavelength and sweep it through, or you can do what they've done there and you have a continuous spectrum and you just look at what goes missing. And emission, you just pump some energy in form of heat or electron. And when I say you pump some energy, I don't actually mean you have to physically do it. I just mean the environment, nature has to put energy in somehow. And because, of course, we're going to get to stars and stellar clouds. So, yeah, you kind of don't need to do it yourself. You just need something with an energy, well, enough energy in there. So my spectrometer, how do you might think this will get complicated to see, or maybe you think it's simple, but here's the setup that I did for undergrad. So this wasn't even proper research. This is a nice little test one. And this is what you also saw in the beginning picture. Now you have a light source, which in the initial kind of thumbnail I showed is mercury. That's the nice blue light you have. It can be anything you want to test. Then you have a number of lenses, and I've done a ray diagram there. So if anyone particularly flat earthers want to have a go about what's going on, you can see this is the ray diagram. It shows you what's happening in each of the steps. So you have the lenses are there just basically to get the light focused where you want it, going in the right way. Now the slit there actually makes an image. It's why when we have a look at it, you see the little lines. You actually pass it through a little rectangular slit, which basically turns everything into a rectangle. When you split them, then you get the different rectangles based on how much the light split. And you can see there that then it passes through a prism, and that will, depending on how much they refract, they'll hit the screen at different parts, and you can just do a bit of simple trig to figure out how much that deflection is. But when you do that, well, when I did it, it looked like this for Mercury, which is a bit hideous. You can see that I've split the different colors, but yeah, they're very close to each other. This is quite zoomed in. So instead, we can be tricky and we can use something else. It's known as a diffraction grating. Now, this is basically where you do the exact same thing, but you do it by basically carving lines into a mirror so that when it reflects, you get an overlapping pattern that gives you the same effect as refraction. It splits the light, except you get a lot of control over it. Based on the density of the lines, you can control how much the light was split for the different wavelengths. And it's the exact same thing. It'll do what the prism does, but it does it in reflection. You also get diffraction gratings, so where you pass the light through and it will split them out. If you ever want, you can hold one up to an old street lamp and you can see the sodium lines. Now, G is just a measure of basically the density of the lines. So in this case, it was 1200 per millimeter, if anyone wants that. N is just it's the node, because what happens is this won't happen once. It'll keep happening. Same with the prism. This is why you get double rainbows. It's actually the same light. It's just you're looking like second order.
Yeah.
You're going one over. And it'll always be dimmer, which is why I'm not looking at it here, because otherwise it gets a bit too faint to see. You always see the first one brighter. So that second rainbow, you'll also notice, is generally more spread out. Like it'll cover a slightly wider area, but it'll be really dim compared to the first one. But in this case, theta is just the angle, and you can get that with just a bit of trig for X and Y. And the reason I bring up the maths is because we're going to tell exact wavelengths. A nice little photo of it, of the setup, so you can see just how simple it is. Light source, couple of lenses, slit, one grating. Grating is probably the hardest thing to get, but you can buy them fairly cheaply online. And then just a little white sheet.
Do you also make them?
The diffraction grating,
or do you does it take a pretty specialized machine to make them?
Yeah, you'd need a specialized machine, so you'd probably have to get them, but they're not that expensive. But okay. I'm talking relative terms, where some things in science can be very, very expensive. But you could buy this entire kit for online from Thor Labs, I believe it is. Some people who've done science will know exactly which company I'm talking about. But I'm not going to advertise for them. I don't remember exactly what it is, but they do. But yeah, this is a teaching kit, but you can do this yourself. You can also use a prism. You can do this with a prism. You might just have to hold it further away and be a bit more careful with how you measure it. It was just, well, we had a diffraction grating, so we get better resolution. You can see things better, but you can do this with a prism. As I said, that was the only switch I made between them, other than where I have the panel to see the light. So, and the lamps are just elemental lamps, but you can test an LED, you can test an incandescent bulb, you can test anything you want with it. Also, you'll notice that apart from the light source itself, nothing's in a container. And that light source wouldn't need to be. I can just put an LED there.
You could have a flame.
Yep. In fact, that was right back at the beginning. That was how they did the original ones. They, not quite a modern look to it, but they essentially did this. A couple of lenses to focus it and to view it, and yeah, flame. And you can even get the metals that you're looking for, as I mentioned. You can spray them onto the flame and you'll see the color and you'll see the bands come up on the board temporarily.
Yeah, or you could have that stuff embedded in the wick or the wax or something, or any number of ways to do it. And all without a container. Amazing.
Yep. So the only thing that's contained here is that light source, and as we just pointed out, you don't need it. If you're wondering, the black panel's just like a laser shield. You just use them it's just to stop the mercury lamp getting onto the panel, just to make it dark so it's easier to see. But you can take that out. It won't change the experiment. It was there, made my life easier in the dark. Because, you have to do it in the dark, which is why photography in the dark is surprisingly difficult when you're looking at one really bright object and you have to try and see other things. But yeah, when you turn the lights out, it's really, really obvious. So hopefully now you can see that the actual color of the mercury there is all of the emission lines emitting at the same time, though due to the dynamics and the energy levels involved, the amount of light coming out is not all going to be the same. Plus, our eyes can't pick up the extreme kind of blue and red ends very well, and then you get off into infrared or UV. but you can see the colors there. And here's the thing. If you have to take a closer look, we've got at least 4 distinct bands. But if I focus on the 3 brightest ones, as I said, I can do a bit of trig and I can figure out what the wavelength is. And so up the top, I have, these are the wavelengths I got with errors. The error just comes from basically the fact that I'm using a ruler and you can only read to a certain resolution.
So you're measuring the distance between the edges or centers of the bands?
So in this case, I'm doing X and Y to get sine theta in that formula. And then I can figure out lambda from it. Because the diffraction grading is set up so that, and remember, n is 1 in our case, because I'm just looking at the first one. I could go to n equals 2. X will just be a lot longer.
That's for additional citation or excitation levels of the electrons, right?
Okay, so
right?
It's actually the same color, but it's the same image, the same stripes, but it's like the second mode you end up with. It's like the rainbow again. You end up with the image repeats itself again and again, but each one gets fainter. So generally you can see 2, but by the time you get to 3 or 4, they go away. And this happens anytime you shine light through a grating, a diffraction grating or a reflection grating as we have here. So the different colors will refract or reflect at different angles. The longer the wavelength, the further along the screen they should be. So the bigger that deflection angle. So all I need to do is get a ruler, and this is all I did in the experiment. I look down at it, I measure Y, and then I go and I measure X. How far between the slit and the screen were the dots? And I can get sine theta. I know what G is, N is 1, and then you can get lambda. And so you can...
Oh, you're not... Okay, so you're not on the screen measuring...
I'm above the screen looking down on it.
You're going from the reflection grating to where it was on the screen.
Yes, I'm measuring how much has the light changed. How much have I deflected it? If it's a longer wavelength, it'll deflect or refract more. It's sort of diffraction, but it is diffraction. It's just we're using a reflection grating and the terms get a little complicated. But this, whenever you have light spreading out, particularly different for different wavelengths, generally that's diffraction. Even a beam like a laser beam will diffract and you'll get beam divergence. And I have a video on my channel where I show that that's a thing. So if you're doing measurements over a long distance with a laser, you have to keep in mind that the laser size at the other end, particularly if you're looking at distances of hundreds of meters or even kilometers, is not going to be the same size as when you let it out. But again, in this case, as I said, it's a fairly simple formula. There's 4 terms. They're not too hard to get. I said you just solve for lambda, which is wavelength. Every time you see the Greek L, that's generally used for wavelength. And in this case, I've reported them in nanometers. But the reason I wanted to show this is that when you go to the literature and you look at what the science tells you, the numbers are the ones down the bottom, and you look at every single one of them was within the error of the experiment. And the error in the experiment mainly came from the fact that I'm looking down with a ruler and I can't be 100% sure of exactly what I'm measuring. If you had some fancy equipment or an electronic panel, you'd get that much down.
You can improve the accuracy.
But yeah, even with just a ruler and a calculator, you can see that in some cases I got pretty damn close. And I said they're all within experimental error, so you can see them all.
Yeah. So
it works. What the literature says, what the science says, is what you can do and what I actually did.
It's great to see the agreement between you're just not reading something and then reporting what you read when it's time to be tested. You are doing the work and verifying that the stuff that you learned is accurate.
Yes, and that's why I like this one, because it works. Because some experiments are very difficult and they don't always match up perfectly. But in my science degree, I did 2 degrees, double degree, but we'll ignore the other half for now. I'll do the science. I did double major. I did physics and chemistry, and they were, in terms of just pure contact hours, I spent more time in the labs than I did in lectures, of course, over the course of the degree. For and that's one thing that I hate is some people say, it's just indoctrination to believe this or that with its anti-vaxxers, flat earthers, young earth creationists, whatever. one, I've met people of all sorts of backgrounds and beliefs in science, so that actually isn't really a factor. As long as the only thing that limits you is whether you can get a science degree is whether you can do good science. If you can do good science, that's it. That's all they care about. And you spend more time proving the methods that they teach you about. You spend more time doing experiments than you do sitting in a lecture. Maybe not so if you add up all the assignments and the exams and everything and all the bits and the study you have to do on your own time. But then again, you also have to write lab reports and do that, and that adds time. But there were some weeks I would spend 16 hours in teaching labs, so in undergrad labs in a week, in 4-hour blocks. So this one here was 3-4-hour blocks to do the full experiment, but it was a lot longer than what you see here. That included alignment and testing a whole bunch of things. I ended up testing LEDs, things like that. But unfortunately, the camera I had didn't let me get a nice spectrum for the LEDs because the silicon chips don't pick up every wavelength very well. But and I've also built laser cavities. I've built a tractor beam before with a laser. You can actually make real life tractor beams, but they're very small and you pick up tiny micro particles.
You can't get a rating ship. Just grab them instead of trying to hit your spaceship.
I mean, if someone's willing to finance me to have a laser powerful enough in space to test it, I'd be more than willing to fire it at a couple of spaceships if someone gets me a laser. But I do like my lasers, and I think I'd just any excuse to fire a laser at something at this point, as long as it's not someone's remaining eye, because be careful. Class 4 lasers, they're the ones you'll be blind before you realize you've looked at them.
Yeah, you don't want that. All right, so we've got, if you don't mind, I've got a comment from a real doctor, PhD Tony, who says, is your guest trying to claim that scientific literature is reliable and replicatable? Next, he'll be
I know it's such a out there and far out statement that it's hard to believe, but my experiment that I did.
Next, he'll be telling us that the sun is mostly hydrogen and helium. Craziness, right?
No comment. Well, not yet.
We'll get there. No spoilers. If I got one more right now. Cretan Bulsa is wondering, I'm joining late and I'm confused. This flurf understands science and could do math. What gives? Just kidding. I think he knows you're not a flurf.
Yes. I have at least 2 working brain cells with a neural connection. No, it's not them that I'm making fun of. Some of them, you can sometimes to hold beliefs like that, you need that much cognitive dissonance. You actually need to be quite intelligent to have the mental skills to actually basically fool yourself like that. But the arguments themselves are as stupid as anything. But I also have more photos and videos too, if anyone doubts that I did any of this. I've got video of me turning all this on and taking photos. But also in science, you don't post that. You post the numbers. It's the results that people care about. And that's why I like this one, because it shows against the picture. Yeah, it works. Now, okay. By the way, I also did the same thing with sodium too.
Back to that last one there. I see to the left of is that blue there, the 436? I see another line there.
Yes. That's just another violet line. It's just another emission line, but it was getting a bit hard to see, particularly vertically down. That's why I didn't focus on it. So for the experiment, I only focus on it. But you could line that one up. And when I actually used a spectrometer, so machines built to do this electronically, you can actually see that line as well as another one shorter than it too. But this is just me showing that the basic principle works, because I do want to get to other, but it also works for other ones. So I like this one because it's sodium. You might recognize this color coming off old street lamps, because they used to be just sodium bulbs.
Okay.
And sodium has 2 bright bands in the yellow. So it looks like one bright one there, but it's actually 2 just very close to each other. But it matches up. And there you go. But you can also see sodium, despite the orange, there's a tiny bit of green there. A little bit of red. But this is one that's used commonly in light. So you can actually, look, it's orange. Okay, we see orange bands. Makes sense. But this is the next bit. This is a full spectrometer that will not only do what I did, it'll do it to a much higher resolution, and it's smaller than a tape measure, or at least the holder for it.
Tape
So it does
holder?
everything I just did in a few seconds, and what's connected to it is an optical fiber, a single mode optical fiber. So not quite the ones that you use in telecommunications, much thinner and designed just to, with a very narrow opening. So it's got a very, very narrow angle of entry. So basically whatever you directly pointed at, it's going to take that light in, do everything I did with the diffraction grading, have a little electronic panel to tell you. The reason I've done it in this order is that I then went on, and I do have photos and videos if anyone doubts it, although at this point I hope not, to actually measure what does it spit out. And this was the output of it. And I've put black lines over those theoretical marks for the bands that I measured earlier. So you're looking at those dotted lines, and you can see that they match up. Plus, there's that violet one. There's the violet one there. And then there's another one that's below 400. Our eyes, this is now in the UV, so I wouldn't be able to see this. You wouldn't be able to see this. We just physically can't. But there you go. There's the one around kind of, there's the two in the sort of the greeny yellow region. Then you get the, that would have been the violet, the blue one, violet, and then ultraviolet. And you can see tiny little dips. That's actually just backgrounding with the fluorescent lights. It's kind of pointed
from the room.
Yes. Okay, so you do, but you can control for it, but you can see the difference.
Yeah.
But the reason I wanted to show this is that I'm going to point that spectrometer at the sun, because I want to show that that black body spectrum that they tell you about is true. And so I just wanted to show that the mini spectrometer gives you the results you expect. Now, yes, they're not perfectly on there, but as you saw, there's always scientific error, and you might get a slight bit off with the calibration. But the black lines appear pretty much where we expect peaks to be, and you see peaks where you expect them. And if you go into the literature and search up multiple papers, you can also find them for the other ones. But I'm just trying to show the three that I showed. And so now we actually have really detailed ones, and you can see how narrow they are. When you see narrow spikes, that's emission, because it comes out at that one wavelength. As I said, the energy needs to be right.
Yeah.
And which means the wavelength and the frequency has to be correct. It has to be the same. It has to be right. You can't be half-assed about, like, you can't be in between. It's like a ladder. You can't step halfway between a rung. So then the Fraunhofer lines, you can show them with this. And if you expand it out and you do what I did with the emission lines, but you do it more detail, these are not my results, but anyone can go and do this. So if anyone doubts these results, go do it. Show us how we're wrong. When you take the emission from the sun, you can just see kind of going left to right, and then going down is decreasing wavelength or increasing frequency. You can see that there's bands missing. There's dark spots. And those are the absorption lines for all the different elements in the sun. Now, I've shown this in emission just because it's a bit easier as a demonstration, but in terms of measuring, absorption is actually easier. And it's the opposite way around. You just try and light through it and see what goes missing.
And the things that go missing are, why do they go missing?
It's because the reverse process of emission. If the light has the same energy of one of the electronic band gaps in the difference in the energy levels in your element, then it will be absorbed, because that process is reversible. If you're talking about molecules, it's not quite reversible. It gets really, really complicated. But when you're talking about elements, which if you're talking about anything as hot as the sun, you're not going to have molecules. Everything's broken into elements.
Yeah. Plasma, right?
And also there's another thing too that we get to consider with a bit of maths later too, while getting sort of closer to plasma. But when you're dealing with, and so that process is reversible. If I know where the light comes out when I pump energy in, if I pump light in, it'll be absorbed. And so this is just when I showed you earlier, you've got continuous spectrum, you've got emission, and then you've got absorption like this. And I can use that other spectrometer to do absorption measurements. I just need a basically continuous light source, so a white light source or something with a black body as well. And then I can look for dips. Everything's just inverted. And I did a lot of that for my honors, where we do that. So I can show the picture at the beginning where we would do Fabry-Perot interferometers and see if we can get the energy to couple. But that's a whole nother story. But if you want to stretch it out, you notice that you get specific bands, and they're labeled with just letters to just associate which band is which. And I don't even remember what they all are. But what's important is that all of those little bands match up with certain elements. Now, coming back to this one, we now can explain the black body, and we can also explain some of the missing bands, but it also explains the red one. It also explains why there's sudden dips, light missing after we pass through the atmosphere. We've got chemicals in the atmosphere. Now, you'll notice for the visible part, whilst there's mini dips, there's nothing huge. It's like, to our eyes, that'll appear white because there's enough of it or whitish without ignoring sunset when you have other effects, which is scattering going on. But if you look beyond that, beyond 700, which is getting into the infrared, you'll notice that molecules that to us look clear now start absorbing at very specific wavelengths. So we know we've got O2 in the atmosphere, we've got H2O, and that's just, when you're in infrared, you can be doing bending and stretching modes, but it's the same thing. If I have some transition that has a certain amount of energy to excite it, if the light has that energy, it'll be absorbed and it'll excite it. And it can come back out, but when looking at light coming through something, it'll go missing. This is the absorption is probably the hardest one to describe from scratch. Hopefully, I'm not losing too many people with it, but it is important to note that the atmosphere has an effect. But we know what's in the atmosphere; you can measure it. You could do what I did earlier. You can just shine a white light source through a section of, like, a sample of the atmosphere and see what goes missing. And then you can use that to account for it.
You can vary things by intentionally adding more water to the air, having more oxygen in there. All right.
And what my PhD in is building environmental detectors, essentially. So I will know what gas I'm looking for, and so I'm relying on the fact that this thing is reliable and repeatable, and I will go out and I'll be like, okay, this wavelength will be absorbed by this chemical, or one of the bands by this chemical. I'm mainly looking at methane at the moment. Okay, so let's see how much light goes missing. And exactly how you measure that, you can get very, very creative. I basically make methane sing with a laser. But I'll make a video on that eventually, but it'll probably be towards the end of my PhD when I can actually say I've done it. At this point, I'm still proving it, which is the whole point of a PhD. But we know what's in the atmosphere. We can account for it. And it describes why when you look at the yellow one, I know it's a bit hard to see, there's all those dips. If I measure this, if I take that same spectrometer and I point the fiber optic out the window at the sun, it's also what I see. Now, you'll notice that the scale and the shape is slightly different. That's also mainly because of my y-axis here. It just counts, whereas before it's irradiance. So it's a measure of basically energy per area for given wavelengths. And that's one common way to do it. You can also do intensity too, I squared. So these are fairly arbitrary, but you see that same shape. So not only can I check that what they're telling us is correct, we measured it. You can actually see some of the bands from our atmosphere as well, but you can see the general black body outline.
So for reference, what is this?
This is when I pointed the spectrometer at the sun. This is what we measured. So when I got this one, the spectrometer, and I can show that, it matches what I measured earlier, so it seems to be doing the right thing. If I take that and point it at the sun, this is what we get.
All right.
This is what we expected. Yeah, so it also matches up. So it looks like the spectrometer is doing its job. It looks like what they're telling us in the literature is correct. I know.
It's
science
quite
is
something
correct.
that the reading in the books and the actual usage of it in reality matches. It's not just reading it and reporting it back. It's actually going and testing it. And I think that's an important thing that a lot of people that haven't gone through higher education miss, is that you don't get to just sit and read a book and report on it. That's not it.
Yeah, they don't just tell you what to believe. What they'll tell you to do is how to do science. And then you'll go and practice it. And you will practice it. And you will practice it. You will test it. You'll be tested on it. And you will also do the maths yourselves. And if you're doing, say, physics, you'll have to learn programming so you can simulate it yourself and show that you know the maths and how to predict these things too. Because, yeah, you can simulate all of this, although the maths here is simple enough that you can just do the maths. You don't. But there are some times where the maths gets too complicated and you have to simulate things. And one of the equations later I'll mention, I actually did do that, though I don't have the results for that here because I couldn't quite find the assignment because, again, it was undergrad physics. But
okay,
yeah.
So I think it's important to say this again, that you can, with this instrument or anybody else can, measure what's in the atmosphere. So you know what's in the atmosphere.
Yeah.
Right. You don't have to.
And then you pointed at
somebody
sun.
else is telling you what's in the atmosphere.
Yeah.
You can verify it for yourself.
Yeah. This is the reason I put this in here is it's not the best image of the sun, but it's me testing it to show that when they tell us this is what the spectra from the sun looks like, I can confirm it. Yeah. Again, notice the shape is slightly different. That's to do with accounting for the axis, but you can look at where the dips are. And if I had more time, which, you know, I have to do a PhD, so I'm somewhat limited in that, I could go through and I could actually be incredibly thorough. I could take measurements of the atmosphere. I could normalize it. I can then fire them directly at the sun. This one was just through the window. So that's also going to cut out some of the UV. Glass will start to block UV. So that's why we're probably missing a bit of some of the shorter wavelengths as well. Plastic's very good at doing that too, even clear plastic. So you'd need to, if you still wanted to fire it through something, quartz, you'd need quartz to fire because that won't absorb. But ideally, you could just take it outside. But, you know, this was kind of tied up to computers in the lab, and I had to get back to my PhD. So this only took me 20 minutes to get. And both of them.
The windows in buildings tend to intentionally choose things to block certain wavelengths. Right? You don't want UV light coming in to your house or your building where you're living and working necessarily, right?
Yeah, and I don't know what the windows are coated with, but even still, for something where you haven't accounted for everything, and I said it's very easy to do it if you want to prove me wrong, you either buy one of these mini spectrometers, although that, despite being that small, it's still about 12 grand, mainly because it is small. You can actually buy a bigger one at a bit cheaper price. But as you said, as you saw earlier, you could build one. Yeah. You can do this. You can make one of these. You can do it. What I said, it's a couple of lenses and a prism.
If you don't trust that somebody else built it right, you can build it yourself. Somebody got to the point where they're at, starting from the beginning, and other people could do that if they really wanted to, because they didn't trust anything anybody ever said.
And if you want help setting it up, if I can spare the time, send me a DM. I'll let you know. But I said, if you actually want the instructions on how to set up the previous one, you can actually look them up on the company's website. I won't rehash it here. But yeah, these are all freely available. No one's hiding it. You just have to know where to go look. But as I said, I only put this one in here. As I said, it's not the greatest one of the sun, but it shows that, okay, I measured and it matches what they said. But if you want to take a more detailed one, all of those little dips and things, those are the black bands that we're seeing, where there's light missing. And now this is where we can start matching them up. We know what the emission lines are for a bunch of elements. I showed at the beginning that we know where they are, the emission and absorption lines. Now, when we're dealing with the sun, basically what's happening is the sun is really hot and it's radiating out, and then things are absorbing the light before it gets to us. So we get to see the outside of the sun. And we can see here that we've got a whole bunch of things, including calcium, hydrogen. Notice helium. I notice helium is in here, but we are narrow, but they haven't shown every single one of them. But helium, the reason it's called helium is after the Greek word for the sun, helios, because helium was discovered in the sun using spectrometry before it was discovered on Earth. It's one of the, I believe, one of the yellow bands. If you want to see more of that, I did mention that in my 10 random science fact videos, so I've got a bit more there. Sorry, I don't mean to keep shilling my channel, but I just realized that I actually definitely cover that in more detail.
The link to his channel is pinned in this.
But yeah, I will give warning. My earlier videos are pretty terrible because it took me.
Just watch the most recent 10, maybe. So I think it's interesting here. You've got calcium, you've got iron, you've got sodium, and it's not very difficult to figure out that we don't have lots of iron just kicking around in this form in the atmosphere.
Oh yeah, this just tells you what we've got. the next bit is how you actually tell how much.
All right.
Now,
But I think my point is it goes back to the previous point of knowing what's in the atmosphere. We know what's in the atmosphere, and it's not a lot of iron.
Yes. So when we see things like this, and we also know we don't have much hydrogen. Now, here's another thing that the FLIRT's always annoying me with is when they say that, say, hydrogen and helium defy gravity. No, they don't. Gravity gives you an escape velocity. It's what, a half... it's square root of a number of terms. It's actually fairly simple. But the maths tells you what escape velocity is. Now, when you have a bunch of gas molecules in a system, I'm not going to say container because that system can be open. It doesn't matter. The average velocity will be a result of the temperature. But that's average. Like if I throw a bunch of balls into a ball pit and keep shaking the whole thing, or let's say I have a little container full of marbles and I shake it, they might have an average velocity, but they'll be smacking into each other. Some will have more energy than others. And when you actually plot out the distribution of velocities for the lighter elements like hydrogen and helium, most of them are well under escape velocity, but a tiny fraction are above, which means all the time there is a small amount that is moving fast enough to basically launch itself out and never come back. And that's what's happening. That's why the lighter elements do that. But as soon as you get to the heavier elements, you don't actually get the distribution crossing escape velocity. You can't pump enough energy into them at the temperature of our atmosphere to do so.
So PhD Tony comes in with the formula V squared over R greater than G, gravitational constant, G M over R, and M is the mass.
I was trying to think of it in just terms of V. So you end up with square.
And that's when you think about it, that's very intuitive. How that happens, yes.
Yeah, basically, the heavier the mass you're trying to escape from, the faster you need to go, and it doesn't matter how heavy you are. But and of course, the further out you are, you don't have to be going as fast. But the thing is, you can do that for gas too, and it works. So we know there's not a lot of these things in the atmosphere. So that's also one of the ways that you can tell that when we're looking at them, where this is coming from the sun. And so these are the absorption lines. Now, in absorption, if you're dealing with low concentrations, the maths to figure out how much you have is very easy. If you can calculate for a given concentration, given path length, this is the absorption I'm going to see. Might have to take a few measurements to get that, but you can calculate it. So all of these, even if they were in our atmosphere, it's pretty easy to correct for. We know how thick the atmosphere is. It might take a bit of modeling, might get a bit more complicated, but hey, that's physics. All the easy stuff was done already. If it was easy, we wouldn't be doing it.
The easy stuff was done,
yeah.
That's a software thing too. All the easy programs have been written.
Yeah. It gets more and more complex. Oh, yeah, there. All right, now where are we up to? However, I want to put this one in here because sometimes when you're looking up to the stars, that's not what you see. You, instead of seeing absorption lines in a continuous spectra, so it's a black body one with dips, you see black body spectra with emission lines. And it's like, okay, well, that's because I haven't quite accounted for everything. And so this is where you get to talk about thick and thin, optically thick and thin. And I did want to cover this because otherwise, if you're looking up at the stars and in stellar bodies, particularly if you want to understand what let's say James Webb is looking at, this stuff is very useful because you need to know which one you're going to get. If you've got something optically thin, what that means is that light passes through easily and you're not going to get much absorption. So to us, if it was optically thin in the visible, then it'd basically be clear. So if it's hot and you're not getting much absorption, then we expect lots of emission and we don't expect it to be recaptured. So you have a very thin gas cloud that's really hot in astronomy. So we're looking at, say, a stellar nursery without looking at the stars themselves, then that's the kind of thing you might see. Very thin gas, but very hot. Optically thick is basically you get light just absorbed very, very easily. So I guess this drink bottle here, ignoring for the fact that the green screen is working perfectly, would be optically thick because light absorbs it. And of course, things like the sun are like that. And you end up with two cases. If the temperature outside, like the further you move out, is hotter than the inside, then you're going to get more emission as you go out. And so you expect to see black body spectrum with emission lines on top of it. And if you go back to the figure that I showed earlier, it's actually, I believe, from stars in a stellar nursery. So it's actually stars burning with a really hot gas around them. So I think it's one of those weird scenarios where you actually end up with case one. I can double check that, but it is exactly what you expect.
It's adding.
Yes, we're adding to it.
Yeah.
Either that or you're going from an optically thick source to an optically thin. But the reason we know that the sun is what we expect is because of case two. If the temperature is getting lower the more you go out, so the T out is lower than T in, and there's a whole bunch of formulas that go behind this, but I'm not going to go through them here. You're going to get less emission as you go out, but you still got a lot of absorption. So instead, you expect to see a continuous spectra with absorption lines. And that's the sun. If you think about our sun, it gets cooler as you go out. It's still very hot.
Yeah.
But that's why with the sun, we expect to see what we see, and some other stellar bodies you don't. But everything that we see is exactly what we expect to see from the maths and from the experiments that you can do. By the way, I bring these up. I'm not going to do the maths here, but I bring these up because I want to scare some flat earthers, because if you're dealing with entropy, then you're generally dealing with Boltzmann. Boltzmann distribution tells you where all the energy states will be. So as I mentioned, when we're doing absorption and emission, we're moving between energy levels in a molecule. Now, for a given temperature, if I know where those energy levels are, then that top equation tells me the ratio between each of the energy levels, how many atoms are in there. However, most of them will be in the ground state. I think to get 50-50 between the ground and then the first excited state in most elements, you need a temperature in the order of about 90,000 Kelvin. So 90,000 degrees, which, yeah, no. So we don't really expect to see that, but it just shows you get a lot of energy out. You don't need many of them to be excited. But because of this, if I know what the distribution is for a given temperature, I know how many in the excited state, I can actually figure out exactly how much emission we expect to see. All I do is I sum the equation, I go over all the energy levels, and the contribution becomes so small that you only need to do the first few, and then they disappear. And you can measure all the numbers experimentally too. But all this is, N is just the number of, like if we're talking about elements or atoms, the number in state B and the number in state A. And the rest are, for the sake here, constants. The other one, though, and this is because we were talking about plasma earlier, is the Saha equation. This tells you how many get ionized, tells you how many you start ripping electrons off. Because when you do that, you change the electronics and you actually drop it. So when you balance them, you end up with a peak, and you can see this would be the optimal temperature to get the maximum out of an emission line or the maximum out of a certain transition. So even with the sun, if you actually look towards the corona, so you don't look directly at it, you can sometimes see emission because you get the hot bits on the outside without passing through the rest of it too. So you can use these two when you're looking at stellar bodies that are way, way away to get the exact temperature, because you balance those two equations and you can tell how hot it has to be to give you the bands that you're looking at, to give you the strength of the peaks. And this one is so simple that this was just an undergrad lab, computer lab. The maths is easy.
All right, so I'm not familiar with these equations, but
I'm not expecting anyone to be. I just bring them up to say that you can do this. You can go back and you can figure exactly what you want to see. And unlike a lot of astronomy, because we're looking at things far away, you can't always be exact. Astronomy is not the most exact of science, unless you're dealing with this sort of spectroscopy. Using these two equations, the only takeaway I really care about people getting is that you can predict exactly what you're going to see.
That's something. And
like the
then
exact strength of the light. So you can actually tell the temperature of things that are far away. And when you look at the temperature of most stellar objects, you can tell that they're not in a dome anywhere close to us because they'd be too hot that they would have fried us. Also, the black body for the sun is about 5.7 thousand Kelvin, which again, if it was only,
it's I think
10 to 20 kilometers up, we would all be
than
dead.
that, I think.
Yeah,
so
I was being a bit generous.
This is interesting too, because there's the red shift, right? So the entire spectrum will be shifted, and so
Yes.
you can still see all the do the work to see where they're at, but they're shifted, and the amount of shift tells you something when you're doing astronomy.
Yeah,
because you know how far away it is.
Yeah, and because we know that for certain elements they're going to emit at certain wavelengths, you could use it to tell redshift. Now, there are, in astronomy, you tend to use what are known as standard candles, which are I think the S1, A1, I can't remember. So I haven't done astronomy for a little while, but it's basically a type of supernova that we know what the spectrum looks like. We know what the flash looks like. So we go looking for them. And based on their brightness, because obviously if the light source is closer to you, it'll appear brighter. If it's further away, it'll appear dimmer. Plus, we can use the redshift, because we know what it should look like if there's no shift. We know what it looks like with shift. We can not only figure out how far away it is, but we can figure out if it's moving towards or away from us. And the supernova basically comes when you have a star that's cannibalizing material around it, and eventually it builds up and then it blows away, and it happens in a very cyclic manner, and because of the physics involved, there is a limit that you reach when that supernova occurs. So it's very predictable. And
so,
from what
if I can do this again, so you know the temperature of something because of these equations.
You can do it from these equations. You can also do it from the black body, as I mentioned earlier.
So you can get within, you can get the temperature of something. And when you know the temperature of something, you know how bright it needs to be, because there's only certain ways that fusion works within certain ranges.
Yeah.
Right. And then
again, there's a lot that goes into it, but essentially,
we're simplifying, right? And then based on its brightness and the inverse square law, again, a different way to get how far you are away from it. Two different ways to get the distance.
Yeah. And that's because one of the things that they used in astronomy to make the first map of the universe, they just used parallax, and they didn't know that galaxies were a thing, so they thought everything were just stars, and so they were a fair bit off. But parallax only gives you things that are relatively close. You're not actually going to see other galaxies. Whereas when you start using particularly the supernovae stuff, because it's such an exposure. Pretty sure from what I remember of it, it is a black body. You can tell how far away they are. That's how you have to use something like that. You need a standard candle to see further. They're not. I mean, I'm trying to cover a lot of astronomy very concisely, which can be difficult. But anyway, you can go look these up. You can actually find, if you Google balancing Boltzmann and Saha, you'll actually find a tutorial for a computer lab where you can actually run the maths, and basically you come up with your own element with its own properties, and you predict what its emission spectra should look like. And you can do that with these. The other one too is that, one more point of mental blank. But it is really cool, because the other thing too is the redshift tells you that things have been moving for a long time as well. So the redshift tells you a bunch, and if you can tell what the redshift is, that's very, very useful. And James Webb, obviously, there's a lot of that involved, which is the last thing I guess we can try and cover before questions. But to me, when I'm looking at astronomy, one of the things that I guess, to steal a phrase that it's not, I guess, the one that I find suits me the most, but gets me in the feels, is when I look at some of those pictures, and when you look at the redshift numbers and you realize just how far away they are and how far back in time, that we'd say James Webb, we could be looking 13 billion years in the past.
Yeah, everything that it's getting is redshifted out of our vision, right?
Hmm.
It's
Oh
only,
yeah, I'll
as I
yeah.
understand it, it's only in infrared. None of what
Yeah,
James Webb is doing
James Webb
is
can't
visible.
see in the visible. It
Yeah.
does not have the equipment. Also, if you pointed at Earth, you'd fry it in a nanosecond. You'd fry all the detectors.
Yeah, it's
It
specifically
has to
pointed
be
away.
kept at about minus 200 and something degrees Kelvin. Sorry, not Kelvin,
No,
Celsius.
Yeah,
So it's only a few Kelvin because it needs to be so cold because it's infrared.
that's why it's got those
Uh,
5 mylar type
yeah.
shields
Oh,
that's
those
blocking
things
the
are
heat.
mind blowing. They just look like foil shields, but they're not. They're built in a way that it basically reflects the radiation out. And they had the amount of points of failure that could have occurred along it. I'm surprised nothing went wrong.
The amount of testing and calibration they did on that is amazing.
Oh,
I forgot the Smarter Every Day. The guy Smarter Every Day, forgot his name, but his dad worked at the place that built it, and he had some video of showing the actual process of doing the testing to make sure that it was the right size and had the right tension and things like that.
that would be. I would have loved to have gone and seen that. I've been in clean rooms before, and that looks like they're doing theirs in a similar way. But I'd love to go see that. But yeah, the research group I'm with has built satellites, but they built CubeSats, so basically tiny ones, and try and build detectors to look back at Earth. But yeah, to look that far out, you need a giant ass detector. But talking about James Webb, so yeah, since we're talking about the layers, those are the ones I'm talking about. But the detector itself has to be even cooler. So they have a cryogenic pump that's really cool. It uses sound waves, uses the standing wave to move the temperature about. But I'm not here to talk about that section of it. It also explains why the panels can be gold without affecting the image you see. They're gold to us, but we don't care about the visible part. We care about their color in the infrared.
Yeah.
And you'll hear it quite often in astronomy when you're talking about color. It doesn't, not just astronomy, but in spectroscopy, color doesn't just refer to the visible colors. I often use it to describe different wavelengths in, say, infrared. So yeah, James Webb is taking similar principles, absorption, emission, and it moves them to the infrared. Now, in this image here, I like this one because it's a good, this one's 16 million. So 16, is it 16 or 4 light years across? It's
I don't
huge.
know offhand.
I think it's 16, and each section is about those sections of it. There are 4. But what we're looking at here is stars in stellar nurseries, so down the bottom in the kind of thicker cloud, and they're forming. And then as they start to ignite, then they start blasting the stuff away from them. And that's exactly what we see. And of course, you can use spectroscopy on it. I'm really curious to see, even they're starting to come out now, but I'm curious to see the papers on it, see what they say. But another little interest to people, if you're looking at a picture and you want to tell whether it's James Webb or, say, Hubble, look at the stars. If it's James Webb, they have at least 6 points to them because of it's the
mirrors
artifact of the imaging. Hubble has 4. So the fact that we've got 6 big ones and then you can kind of see 2 on the horizontal along here, that tells you that this one is James Webb. So that's a nice, cool little one to tell the difference between them.
As I understand it, those are the ones that aren't in focus. And that
you could be correct.
Ones don't have that effect.
That would seem correct, but I'd have to double check. I'm not sure. The astronomy side of things is more of an interest. I'm more set on the ground, but I still find it interesting what you can do with it. But the other thing too, and this is why infrared is so useful, is this one. This is also, again, because you can see the stars, you can tell that this one's James Webb. Now, in the one on the left, this is the near infrared. So these are wavelengths that are close to the visible or closer to the visible. And you can see a whole bunch of debris that's been blown out from some event, and you see one bright star in the middle. And whilst you might think that all that debris comes from the bright star in the middle, it's not. When you actually switch to a longer wavelength, when you go further into the infrared, less dust particles get absorbed. You have less absorption. You can basically see through material. Things become transparent. So if you want to see into dust clouds, if you want to see through things, that's why infrared can be very helpful. Because if you know what colors, things will be absorbed and emitted. Well, you can just basically you can do the opposite. If you don't want to see them, you just move to where you don't have as much. And so when you do that on the right, I believe it's mid infrared, you can actually see two stars in the middle there, and it's the smaller red one just in the center there that's done all of that.
There's two, yeah.
Yeah, it's the one that's done all of that blowing off of stellar material. I believe what's happened is actually you've got a younger bright star next to an older one, and the older one is, I believe, dying. I think about half of all the stars in the sky are binary, so there's two of them. And so you get all these cool dynamics between them where they basically cannibalize each other, and you can get events like this. It's really, really cool. But I bring this one up because knowing about this, you can also go the other way. You can do more than just, I want to know what materials there are. It's like, no, I want to see through the materials. Things that have color to us or are invisible to us, not necessarily the same in other wavelengths. It's also why you do a lot of astronomy using X-rays and gamma rays, because you'll see other things too. And radio waves. Radio astronomy is a huge thing. And those telescopes are so sensitive that you cannot turn your phone on, turn Wi-Fi on when you're on the premise, and they're like square kilometer areas.
Yeah,
like they're huge, like farm area sizes in the middle of nowhere, and they'll know if someone switched their phone on because they're that sensitive, because they're looking for tiny signals. That could be in faraway galaxies, and you come up with a radio signal from your phone when you switch it on, and the next thing they know, they've got blip.
Yeah. And they tend to have arrays of antennas too.
Yes, there's by having multiple of them, you can increase the resolution without needing a dish that's the size of the distance between both of them. So you can effectively build a radio telescope with I guess the radio equivalent of a lens bigger than the diameter of the Earth. You just need to position some antennas very carefully, and if you put one on the moon, then instead of just being like the radius of, say, a satellite in orbit versus the Earth, you can have it as like basically a telescope the size of the diameter, basically the Earth and the Sun. So the Earth and the moon. Yeah. You can actually build the equivalent of giant telescopes with it, and I'm curious to see, because I've heard plans for it. There's but I'll need to have a look at that.
Maybe just proposals. I don't know.
This stage they are.
Yeah.
They're not quite close to it, but it will be really cool to see it, and I'm sure they'll do it. And people have been working on it. But they're already doing the basics of it. And as you said, you have arrays, and you can get the same thing by building an array. You just spread the array out over a much wider area.
But
that's
true.
I deal with the infrared. That's my area of expertise, and I do a lot of teaching with UV vis. So those are my areas. But this is the bit that comes back to what I do, and detecting gases on exoplanets. So this was a hot gas giant exoplanet, so WASP 39b, and this was different detectors on Webb, and then when you put them together, you get this thing. And you'll notice that yes, there's a huge amount of error in them, but you can do a lot of maths to correct that one out. You can see, because remember this one here, and this is where it might get confusing, is in they say amount of light blocked, so absorption. So this is looking at how much light goes missing. So the higher the peak, the less light is coming through. So it's basically the flip of what I've been showing.
Yeah. Okay.
Which is also how you'll see it. It's quite common to do absorption that way, where the higher the peak, just because.
So this water.
This one's just detected water. Yeah. So they've detected water in the atmosphere of an exoplanet. Against the sun, because as the light from the sun passes through the atmosphere, the water absorbs certain wavelengths, and you can see the absorption peaks of water, because again, we know where we expect water to absorb. Now you'll see here we're actually in the infrared. That makes sense. It's James Webb, and so we're looking kind of. I think this is So this is still vibrational modes of water here, and so you're not quite at what a microwave will do, but we can see the water peaks. Yeah. And they're quite consistent. You can, by measuring multiple of them in one go, then you can be pretty damn sure that it's not just background fluctuation. If you want a good example of not being able to see much against the background, look up, that was the whole Venus and the phosphine on Venus thing. They were even further into they're in the microwaves. They were looking at a rotational mode of phosphine, and it was a tiny little blip that they saw, and correcting out for the background turned out to be a bit more difficult. It's almost certainly phosphine. It's just probably not as much as they thought. But if you're wondering what the whole, we might find life on Venus, that was what that was. But I've talked to astrobiologists who say, yeah, no, not on Venus. The atmosphere is like pure acid. It's not friendly to life. They say there are sections of it, but I'd say we have a better bet for life on, say, Europa or Enceladus, something with a subsurface ocean. But the importance of this is that whilst James Webb's probably not going to pick up life or the evidence of life, when you do have life, it does tend to leave byproducts. For example, oxygen is not a naturally occurring gas because it's unstable. It'll get burnt away or reacted into something else.
Yeah.
So generally, if you see things like that, methane's another one, depending on the concentration. Hence why there's the whole thing about trying to detect methane on Mars. Those can be signs of life. So if you have a spectrometer that is powerful enough to detect the absorption bands behind the glow of the sun, you can potentially detect life on exoplanets. And
what did this find?
This one just showed that we've got water.
Okay, so it's
this
not
one's
able...
not. No, you're not.
I said, like James. Yet.
Yeah, you can, because picking up things like if you've got water vapor, there's generally a lot of it, so you get a lot of absorption. It's a bit easier to see, but yeah, we're looking at like a paper thin layer as a relatively tiny planet goes in front of an incredibly bright star. Okay. To be able to see anything is impressive.
You need more precision to really.
Yeah, and James Webb. It can detect some stuff, but I don't think it's likely to detect life. If maybe something was closer to home and we got very lucky, but you'd probably want to build other things. But the other thing too is that the background becomes a problem. But one of the other chapters that I'm doing for my PhD, I haven't really touched on it because I'm only just kind of starting it. It's one of the smaller sections. Some applications of that one in astronomy potentially could get us there. Allows, but yeah, you'll need other things. You basically need a way to look at all of the absorption bands at the same time. So you basically remove background noise. So you're looking for multiple things going up and down. And if you get one going up and the other one going down, then you know that's background noise. But I like this one because it shows that the basic principle, it's doable. Yeah. We just haven't got to the point where we can pick up life in exoplanets. But it's still
maybe the successor to James Webb. I don't know.
Yeah, I mean,
to be sensitive enough for that.
Yeah, you never know. But James Webb is already showing us a lot of amazing things, and I really want to start reading more of the papers that are coming out because they're starting to come out. But there's always a delay. Whenever you see the images, it will take a while for them to be fully analyzed. So yeah, astronomers, you can't just this is the first thing that came to my mind here. Bleh. No, there's a lot of thorough steps.
Real work to do.
Yes. If it was easy or if it was just, hey, listen to us, then you could get a PhD in less than a year, but it's it's not easy.
If it was easy, everybody would have one.
Yeah.
Or just go to a fake school and print one out.
Hello, my name is
there's a few of them.
Yes.
All right.
That was where I wanted to finish it on because it was sort of I just wanted to tie it in so that it was a bit more cool and modern. So I'm happy to go to questions or whatever you want to move on to. But I think it's a nice one to finish on where it's kind of start this journey of how do we know that spectroscopy works, and then what can we do with it? And I said, I've only touched on a tiny area of spectroscopy. There's a lot more. But hopefully it's been interesting, or at least it's provided some useful information.
I've enjoyed it. Okay, I've got a few questions.
Okay, good.
People, if you have questions, tag me, and I will get them out.
Also, do you mind if I stop sharing? Then I can also have a look too.
Yes, go ahead.
All right, I'm gonna do that, and I can bring
All
that
right.
back
We've
up
got
place.
Crumpy Old Grunt says the fine constant 1 over 137. Can he help me? As I just divided the speed of light by the constant, and it matches the electron velocity in a hydrogen atom of 2,190 meters per second.
Can I see the text for that? I think I'd have to actually look at that for a bit longer to give an answer. The only thing that comes to mind briefly is that you can derive the speed of light in a vacuum from universal permittivity and universal permeability, or 1 over the square root of the product of the two. So there are sometimes things you can do, but I'd have to have a look. Probably have to spend a lot more time on that question.
I'll send you that. It's from Crumpy Old Gunt. But I don't, sometimes things are just coincidental. Sometimes they're not.
Yeah, that's always the case. And also the other thing too is that science, if anyone tries to tell you they're an expert in science, you know that they're pulling your leg, because you can never be an expert in science. You're an expert in one very, very narrow area of science, because there is just too much to know.
Yeah.
You can't know an entire field even. Like, I can't know all of spectroscopy. I don't have enough years in my life. No one does.
No.
So you focus on either what interests you or what you're good at, or some combination of them.
So a question, is it true from Stringer News 1, is it true that spectroscopy containers are just old mason jars? Asking for a friend. I don't know. Oh, I happen to have a mason jar handy.
No comment. No. Let's not incriminate ourselves. Shh. The Illuminati can't find out.
We've got a very serious one. It says, what's the escape velocity of an unladen swallow? Again, that's V.
It's 11.2 kilometers per second from the surface of the Earth, because everything has that escape velocity.
Yep, even a swallow.
Yeah,
laden or unladen.
And if it's laden, it doesn't matter. As long as it gets up to that velocity, it will achieve escape velocity. It doesn't know how much it's carrying. But you might need to have a few swallows with things on lines between them so that they can achieve the velocity. But there we go.
And that's discounting for air resistance. Cat Poke says, I have a question for Almost a Doctor. Do you think the amount of phosphine on Venus is enough to potentially be indicative of life?
The difficulty with this one is actually determining how much. The signal that they're measuring is incredibly small. It's like the distances in astronomy are just insane. They're just incomprehensible because our brains didn't evolve to really understand that. And so the actual bit of the atmosphere that you're looking at compared to the size of the planet, and then the distance it is, and the fact that Venus is often very close to the sun when we're trying to view it, you do get a lot of background. Trying to spot that band is quite difficult. So the reason I can't really give a definitive answer is it's really, really hard to tell exactly what we saw, or at least what was seen. I've read the paper. I think them jumping to the conclusion that it means there is life was very premature. But even when you read the paper, they don't really present it as the only opportunity. It's just, hey, this would be one really, really cool thing, and our numbers match that possibility, but they don't say it definitively. And I think like a lot of things, when you go from science papers to, I guess, kind of general media, things get exaggerated a bit for the sake of making a good story, and that's what happened. Yeah. I've seen some papers that suggest, or at least there was one paper that suggested that it wasn't even phosphine, but that one's already been debunked. I actually had the opportunity to talk to a astrobiologist on this one, and so they thought it might have been SO2, but it doesn't look like so. It looks like we've detected phosphine. The other thing too is that other studies looking at other data have come back with much lower numbers, and some of it being present is fine without life. Is easily accounted for by natural ones. So it's so far only one result that seems to show this really high number. Well, like one series of results. So this one group and their saga. If it is that high, possibly, but it looks like it probably wasn't that high. But the other thing too is, what if we're looking at different parts of the atmosphere? There's nothing to say that the whole atmosphere is going to have the same concentration.
Yeah.
So there's just too many variables. My personal feeling is no. As I already said, I don't think Venus is going to have the most friendly atmosphere. If it does come back and we have better evidence in the future when we send probes there, that there might actually be more to it, just like Mars. They had the exact same thing with methane on Mars. We had probes that kept picking it up, but there was a whole debate about whether we had enough methane. Then we actually landed the rovers on Mars and picked up methane. And the methane on Mars is actually seasonal. Goes up and down with the seasons.
Yeah.
And some people have suggested that's an indication of life, but it is completely explainable by very, very low energy.
So you don't think it's cow farts
activity?
Is it what you're saying?
Moon cows that got displaced onto Mars somehow. But
they got caught jumping over the moon.
Yeah, they went a bit too far. Yeah. They went a bit too far. They because the escape velocity, they just kept going. They didn't slingshot back, and they ended up crashing into Mars. But most of them were unlucky because hitting Mars is, like two hitchhikers being picked up in the vacuum of space. All
right, let's get another one here. Fish and Stew says, "I'm a moron. Please explain black body spectrum and radiation and how it pertains to spectroscopy."
No, it is quite difficult. Spectroscopy is not easy, so being a moron has nothing to do with whether you got it or not. Everything with a temperature emits black body radiation, and so when you're looking at things in spectroscopy, if you're looking at something that's really hot, which you often are when you're dealing with astronomy side of spectroscopy, then you're going to be seeing a black body spectrum. So it just helps to know what you're looking at. And so the bigger it is, so the higher the peak, and also the bluer that peak occurs, so the more bluer that the overall light is, then the hotter it is. And of course, the hotter you make it, then it goes both ways. And so that's what the formulas I was showing were. It's just basically when you have a really hot object, what does it look like when you map it out across the different wavelengths, and you get that nice kind of distribution. And that was what Planck was famous for. One of the things he was famous for. Some people also consider him one of the fathers of modern quantum mechanics, which, as I said, is quite ironic because he didn't believe in quantum mechanics. He didn't like them. He didn't like the result. He said, look, the maths works, but I'm not happy. But because he was a good scientist, he's like, no, I'm going to go where the science leads me. Amazing. And it turns out that he was correct, even against his own intuition.
All right. On the black body topic, the people have bounced radar off the sun. And other people have said, oh, but the sun is a black body, therefore it only absorbs. So can you explain a little bit what they mean when they say the sun is a black body, and how that impacts the ability of the sun to reflect radar?
So a black body is just any object, really, that is in thermal equilibrium with the environment. You could model a person as a black body. The only thing is the thermal equilibrium one is where you start moving from a nice theoretical model to then having differences to deal with reality. But a black body just refers to that thermal equilibrium. And when you're in thermal equilibrium, you'll be giving off radiation at certain wavelengths. It does not have anything to do with what will be absorbed. To be absorbed, you need some mechanism for that light to be absorbed. So you need some material that will absorb that wavelength. So one of the ways they actually started testing black bodies, one of the ways that they got the closest thing to a perfect black body on Earth, because there's the whole thing about science of the perfect black body. They basically built ovens where they would just like seal them, coat them black, coat the insides black, and fire them up and have a tiny viewing slit where you can let the energy out and you can see into it to check what the color was, what the temperature was. But unless the actual solid part of it, as much as you can describe the sun as solid, but in terms of spectroscopy anyway, unless it's going to absorb that wavelength, the fact that it's a black body has nothing to do with it.
Right.
Yeah. It'd be the same as saying, I can't bounce radar off metal if I heat the metal up, because, well, actually, no, you can't.
It's radiating.
Yeah, it'd be like, it wouldn't matter. I wouldn't have to heat it up. It's got a black body spectrum anyway.
Yeah.
But we know we can. That's the whole point of radar.
I think the confusion is that it's more about what it's outputting than what it's absorbing.
Yes. The energy to output comes from thermal stuff, and how you feed it that thermal stuff. Well, that's a good question. But if it's not going to absorb radio waves, well, they're just going to reflect off. I don't know where they got that, but then again, when it comes to some of their arguments, you don't know where they come from.
Yeah. All right. Delco says, "Ooh, Toon just said Gunt." There you go. It was a guy's name. Sorry. Whatever. Let's see. Got a couple more. I'm moving through to find a couple here. This is a good one here, but it's off topic. I'll just put that up to enjoy the little poke.
Well, we kind of did poke at him too.
Yes, Dearth. So Dearth said when he was debating Professor Dave that spectroscopy needs a container, and here we have somebody who does spectroscopy. And do you need a container?
You don't need one. Container is optional.
All right, we got Lubo in China says, "Can you ask him if he has his own astronomy setup? What is it, and if he could recommend any astronomy filters, as there are many inconsistencies between the consumer-rated filters?"
Unfortunately, I do not. The astronomy work I've done has actually been for other astrophysics groups at a university level. I don't actually have a setup, so unfortunately, I can't really help you on that. There's so many hobbies I wish I had, but
maybe Astronomy Live would be the channel to go to there. He specializes.
Yeah, I wish I could help. Most of my stuff is a bit closer to Earth. It's just that a lot of the theory that I deal with, a lot of the experimental side I deal with, has applications in astronomy. I am technically part of an astrophotonics group, despite the fact that I'm not an astronomer, or that I don't work in astrophotonics. I just work in areas that are very close to it.
All right. We've got Space Gazette says, "Can you explain more how we know the contents of our atmosphere at different locations, especially how far our atmosphere reaches into space?"
Okay, so this one does get a bit harder because you get to a point where it's so thin that you're probably not going to see anything. And so you need other ways. You're looking for individual particles. You might use other detectors. In terms of knowing how much, that actually gets really complicated. And it really depends on the setup, on what you're trying to do. There are some ways of doing it where you can just basically look at the atmosphere without the sun. But a lot of spectroscopic techniques to measure the atmosphere, if you want to look at them, you kind of need a background so you know what the sun is. So yeah, it's a lot of feeding into each other. I'm trying to think of an easy way to do it, but most of it is basically, we know what the gases individually do, and then so we know what they do in the atmosphere. I trying to think of an easy one to answer, but
this overlaps nicely. Maybe this will give a little bit.
I could talk about how I do it, but I'm only looking for one gas at a time.
Yeah. So there's a probe that measured, I think it was doing spectroscopy around the moon, and identified helium emissions of a certain frequency in the vicinity of the moon.
Emission. Okay.
Yeah. And it was because of this specific emission, they were able to determine that hydrogen was from the Earth and not from some other source.
Yes, because as I said, you can predict exactly what you expect to see based on temperature and other conditions too. So if you know what you're looking for, you can just go and look for it. In my case, when I do gas detection for environmental monitoring, so we want to look at how much, say, methane there is in the atmosphere, then I actually find what bands methane absorbs. I find one that doesn't really overlap with anything else in the atmosphere, and then I build a portable detector. And this is what I'm trying to do. So I haven't done it yet, but you would build the detector and then you would move it around, and you'd get the detection at different points in the atmosphere. So you can look. So the sort of detection that I do mostly focuses on how do I know how much gas I've got here, like in front of me. But there are other methods, so column detection methods, where you look at the light coming in and you can measure the gas between you and whatever, I guess, the next opaque object is. And that's what a lot of the people I work with do. They build sort of detectors that will do that, such as CubeSats. So you basically do what I did. You split the light up and you look for the bands, and then you just have the detector move. You can put it in orbit if it's a CubeSat. You put it on a drone. You put it on a truck. You can just carry it. And one of the problems I'm trying to face is that most environmental detectors for methane are not all that practical. So we haven't got small ones that are portable, and we don't actually know exactly how much methane we're releasing, and it looks like it's going to be a lot more than we expect. But you need something fancy like a giant plane with LiDAR to actually map it to any deal of accuracy in that case, although there's another one. LiDAR would work. You basically, you build very specific spectrometers, and then you move the spectrometer around to see how it maps. You build maps. A bit like, I guess, how you could make a thermal image. You know what you're looking for, and then you can move it around and make maps. It's
okay.
It's more of there's so many ways to do it.
Andrew Tate said Venus is too emotional to accurately read phosphane spectroscopy. Maybe you don't just need to. We've got some Calfart detection. We say Thunderfoot at least debunked the phosphine on Venus.
From my understanding, look, it looks like it is there. I haven't actually seen that video from Thunderfoot. Is it as much as they're saying? That's what I said. I lean on the side of it's not as strong as the original detection, but I don't think we're in a position where we can definitively say what's going on. But it'll be, as I said, just like Mars and methane, if you want to go look up that saga. And when we actually land probes again on Venus, that'll give us a much better understanding. We need, this is it, spectroscopy at a distance is not as easy as doing it right up close when you've got the gas in front of you. And
that helps.
Yeah. The only problem with Venus is its atmosphere is made of acid and it's hot enough to melt lead. The longest anyone's kept a probe there was the Soviet Union. They kept it going for 2 hours before the heat got to it. But one of my favorite little stories from astronomy comes from that. It took them about 20-something goes to do it. And one of the first probes to land, they wanted to take photos of the surface, and the lens cap failed to come off. So they didn't get any photos, any good useful photos. Then they sent a probe, and they're like, okay, let's fix the lens cap thing. They'd already had one probe where it was meant to get a 360-degree image photo, send it back before the probe died of heat and acid, and one of the lens caps failed to come off, so they got half it. So like, okay, we'll fix the damn lens caps. They also had a few other things on it, including one which is basically just a needle on an arm, and it just swings out and goes whack. And it tells you about the hardness and the rigidity of whatever it's hit. And you can get a rough idea of what you're looking at. And when they set the probe, the lens caps came off, they got a photo, and then the probe thing came back and it said, there's a lot of plastic on Venus. This is not right. The thing had come straight out and landed on the lens cap.
All that work. Yeah.
Right.
All right, we got Cat Pokes says to you, thanks. I've looked into it a lot and had more or less the same thoughts as you, almost. It's really good to hear from someone who actually knows what they're doing because the topic is messy. So Cat Poke mentions.
And I actually got to talk to someone who actually knows more about this than I do, because they're as an astrobiologist, they're looking for what chemical signatures you would expect to get from life. And their one isn't just one chemical, but what balance of chemicals. However, we're not quite at the ability yet to be able to map out the full kind of, I guess, concentration map of what we're looking at on exoplanets, which is what we need to do to confirm life in other solar systems without physically going there. But we know how to do it. We just need to figure out, like, we know the theory of how to do it. We know what we need to do. It's just, okay, how do we actually build machines and detectors that can do it? That's the difficulty.
Yeah. All right. We've got, does he have any, from Charlie, does he have any comments on forbidden transitions? Shh, don't tell anybody. They're forbidden. These are actually very important in astronomy, and they give insights on interstellar gas density and other things.
So forbidden transitions, to me, I'm thinking about ones that are, because it's going back to what I did for lasing in honors. I think, is he talking about the ones where particularly when the electrons come back down, they can't make the transition because of violating Hund's rule. I think there are certain, like, because when I showed a very simple energy level diagram, you just basically have it as a ladder. But when you start building to molecules, that it's not just a straight ladder. You actually have parabolas with ladders built into them, and it's really, really messy. And you'll have some transitions that are more likely than other, but you tend to get emission and absorption at different wavelengths, all sorts of stuff. But there are transitions when you're building these electrical systems that, based on quantum mechanics, they cannot occur. You cannot have an electron jump from one energy level to another one based on certain rules that we know of. So I'm wondering if that's what Charlie was referring to. I'd have to look more into it before I could give a definitive answer. And I want to be a good little scientist and not pretend to speak if I don't actually know everything about it.
That's fair. All right. A question from earlier from Dr. Nimrod. Actually, it's just a comment. It says, I'm having trouble understanding everything, but that's a me problem. This is very interesting despite me not knowing. Please tell your guest.
Yeah, I've tried to tailor this so if you didn't understand all of it, you'll still get something. Because again, you're not going to understand everything the first time about it, particularly if it's a newish topic. So
watch it again at half speed. News1 is asking, is there a Planck variable instead of the Planck constant?
If you're when you're doing DIY and you get the wrong length and you have to
just
keep going,
put a number in to make it all fit. Clara Microraptor says, as this person done flat Earth debates,
I have kind of done one on a very small channel called Hereticals, where we had some flat earther come in, but that was it was a different one. But I would be happy to have a go at them. I won't take them too seriously. Don't expect me to do that.
Flat earthers are for entertainment only.
Yes. I'm happy to look if someone wants to set one up, as long as it's on a friendly platform, because it's certainly not going on something like any of the Nathan channels, because I've heard some of what they say. I mean, I watch this channel and like other ones like FTFE and even Sir Sickard. You get to see the sort of lovely people that you sometimes deal with. So that's why I said if it's on a friendly platform. But the thing is I would want to narrow the topic down. I'm not going to talk about say surveying or
it has to be in your
rocketry, because that's not my area. But if any of them want to have a debate about how we know the sun isn't close or how we know what the sun's made of, all
right. Somebody asking, is Mallory and Bryant going to happen? Yes, indeed it is. A week from tomorrow. Mallory and Bryant a week from tomorrow. And this one I won't read out loud, but I can agree. Let's see.
I was wondering how long it would take until someone made a joke like that.
We've got track and field needs a container. We've got, is he secretly Gordon Freeman? Are you secretly Gordon Freeman? Every once in a while, somebody asks if I say that I look like somebody, and I'm like, I don't know who that was. So, maybe
as far as I'm aware, I'm not secretly Gordon Freeman.
Okay. All right. I'm trying to spin through a little quicker here. Let's see. Who's this? Squash. I show up to a video about spectroscopy, and the first thing I hear is the guy talking about gases. Hope he doesn't try to claim a container is needed.
Only to hold the drink that you're having while you're doing it.
There you go. How about detecting methane? We say methane in the US on Jupiter, much easier than Earth. Yes or no?
Well, the advantages with Earth is that you can use certain spectroscopic techniques where you can just do it live. So you basically do active testing. If you're doing detecting elsewhere, and this is also why it's been so hard, you're basically doing passive detecting. You're detecting what light is there, and you're hoping that some other background light source has passed through and given you absorption, or if you're dealing with something that's hot enough emission. But if you're looking for planets and exoplanets, there's no way you're going to get enough temperature to get useful emission lines out of it. If you're right up close to it, it's you could do it. But yeah, if you're looking for emission on an exoplanet, there's no way you'll get emission from here. You have to, and that's one of the reasons why I'd say no, it's easier on Earth, is because we're here. I can have my detector here on Earth, whereas on Jupiter, I have to point my detector up and wait and pick up the tiny amount of light that comes from it. It's the reason why, as with Mars, they wanted to send probes, Venus, they want to send probes. You actually want to land things on there. And there was one recently on Mercury that picked up the fact that Mercury actually has like a gas and liquid dynamics to it. You actually get flow and movement of materials. They thought it was too hot, too close to the sun. But do you actually get solid ice of certain materials, not just water, because other things as well at those kind of really cold temperatures, that are protected in the deep craters, because the sun, even though it's like the sun doesn't quite get to the bottom of the crater, so it stays cool enough. And because Mercury rotates very slowly, occasionally some of these craters stay dark for a while, then they get exposed, everything gets evaporated, goes to the cool side, and then finds another place to hide it, solidifies, some of it ends up in craters. And so it ends up with this very brief flow, and they've actually seen like flow marks and things like that. And it's really, really fascinating. I put a lot of effort into that. I made a two-part video. It was the longest one I've ever made for my channel on where we might expect to find life. And one day I'll get a few hundred views on them. Well, but I covered that one there.
Go subscribe. Link in the description, and it's pinned right now. We've got,
thank you very much,
Space Gazette. How do we know space is a vacuum? How do we measure the contents of deep space in general, like as far as the moon?
So deep space is not the moon. Deep space is basically, we're talking further out, so generally beyond solar system. Basically, if we can't reach it, from my understanding, I'm sure there's a more definitive definition, which I probably should know, but I'm going to have to plead ignorance on that. But I know that you wouldn't refer to the moon as deep space. But how do we know that space is a vacuum? Well, multiple reasons. That if it wasn't, there'd have to be material there. If there's a material there, then you have to have absorption, because everything's made, any molecule material will absorb something, but we don't see that. That's one way that you can use spectroscopy for it. And that's
so we know that we know what's in the atmosphere, and we know what gets absorbed, and we can see the effects of that. And we don't see other things.
Yeah. If space was full of stuff, we would see stuff, even if it wasn't visible. And if you're going to claim, and if you want to say that it's full of stuff like dark matter or something that doesn't actually absorb or emit light, well, it is full of dark matter, and that's actually one of the problems. But when scientists say we don't know what dark matter is, that's actually not. It doesn't mean what it might to a lay person. They actually have a pretty damn good idea of what it is. You can even narrow the size of individual dark matter particles down. And we know that if it meets certain criteria, it will appear this way. So we are doing experiments to detect it. How do we detect as far as the moon? Apart from the sort of passive ones where you just look at the light coming in and see what's there, you can send probes. I think that was the one that you were mentioning earlier about how they picked up the hydrogen, which is how we know that the atmosphere extends out that far. And that doesn't surprise me, that one, but it is cool to learn that some of the gas from Earth does reach that far. The main one is that, probes will tell us, but if you want to measure a vacuum, you can do it you can just set a pressure sensor out on a probe and send it out into space, and you can see the temperature drop. But you also don't need a probe. On a satellite, you can launch something up, and it doesn't take very long before you get pretty damn close to the vacuum of space. Because remember, the atmosphere on Earth is, let's say it's a couple of tens of kilometers. Low Earth orbit is about 200 to 250 generally, but it's about 200, 400. You can go a bit higher. I think ISS is about 400 kilometers up. The radius of the Earth is several orders of magnitude bigger than that. We're looking at a tiny fraction compared to the Earth. So the atmosphere is very, very small. You don't actually relatively have to go that far up before you're physically out of it. You can just have a detector.
Yeah. Well, the balloons that go to 120,000 feet, several of them have barometers on them, and it's 0.1% of the pressure as it is at ground level.
Yeah.
And it continues.
The first man-made object in space that actually made it to space was the V2 rocket. In terms of actually getting beyond what the balloons can do, we'd had pictures of the Earth from pretty much space from, I think, balloons earlier than that. But the first actual objects that rockets that man put in space, the V2 rocket, which compared to today's technology are pretty simple. Yes, they weren't back then, but first time you do anything, it's not simple.
Yeah.
But those are, they if you ever go look up, there's a really, really cool video of a V2 falling over on test. It just heels over, and you just see it it just shatters. All the liquid fuel and the oxygen just bursts out and then ignites, and you just it's just like, it's insane.
All right, I need to address this a little bit off topic. We've got Flat Earth Dweller Man, who thinks that Professor Dave won't debate Austin. Professor Dave is happy to debate Austin. He continuously offers to do it on FTFE's channel. Austin is unwilling to do that. So there you go. You let your hero Austin know that you think he should do it. Professor Dave has already offered to do it, and on FTFE's channel. There you go. All right. He's making a lot of noise in the chat. He's making a fool of himself. So, all right. Let's see.
Has he had any?
All right,
I just saw his last one.
The Sun Express says Galaxy Dragonfly 44 is a problem for absorption. It's over 99% dark matter. Okay.
Dark matter is not so when we're talking about spectroscopy, we're talking about general baryonic matter, which does interact with light. The reason it's called dark matter is that we can't do spectroscopy on it. We can't pick it up that way. So we're looking for other ways to detect it. So it's not really a problem. It's like saying that your window is a problem to seeing outside. No, you just see through it. But you're not going to really see your window. I guess it's probably not the best analogy, but that's the problem with analogies. They're not always going to be perfect.
All right. We've got Charlie says forbidden transitions are one way to understand that there is very little matter out there.
Oh,
I'll finish it. These transitions require an excited atom is undisturbed for a long time. No nearby atoms.
I think I know. Yes. So I actually looked a bit of this. So there's a bit of this in my honors work, and I did end up actually publishing a paper on some of it. But you get forbidden transitions where the decay time is increased because when you excite the electrons, because you can fit in the same state. Well, you can have two electrons because spin up, spin down. But when you get excited, you sometimes get systems where they'll have the same spin. So you can't have a direct transition back down. And it might even be more complicated, but you can't always have the direct transition because you can't. They have the same spin. So sometimes you need to wait for things to relax or for that spin to switch back before they decay down. You actually get very short-term versions of this in a lot of optical systems, particularly because I used it for lasing, and it is something to take care of. So, okay, that's actually pretty fascinating. I didn't realize they're looking at that in astronomy but yeah, that makes sense. There would be some transitions that can't occur, so you have to wait for everything to get in the right quantum mechanics happiness before it'll actually decay back down. And by that, let's not disobey Hund's rule I think it's Hund's rule. I am not a particle physicist.
All right. With this one, I'm caught up. I'll leave that unanswered.
Yes, I think that's probably for the sake of leaving your channel intact, we'll leave that one unanswered.
All right. So, well, this has been 2 hours so far. It's been quite something. So I think we'll wrap it up here in a minute. This is your last chance, if you're watching right now, to go subscribe to him. I think I will be putting this on my Conspiracy Tunes channel, maybe a summary version or parts of it shortened, maybe to get a little broader audience. So be looking for it there. I have some stuff coming up tomorrow, but more importantly, Almost a Doctor, can you tell us what you've got coming up and what's going on with you next?
So because of my PhD, I'm getting to the pointy end of it. I can't make videos too regularly, but I am planning to do a few live streams. I have one coming up where I want to take a couple of co-hosts and another person who's appeared on my channel, and we're going to rip the movie 2012 to shreds. I haven't set in a time for that. I've got a few ideas for videos that I want to do that will appear. I want to do one about whether scientists wear lab coats. So I'll go through, well, what does it actually look like to be a scientist? That might take a little while to get out there. But I do want to do, because the last one I made did very well, the rocket fighter, I'm going to do another history-based one, but I haven't quite decided on the topic. But if anyone had suggestions, I might be able to get around to them. But yeah, I wish I could say more, but yeah, PhDs, particularly towards the end, are a bit, make it a little difficult.
It's a lot of work. So I appreciate that you took time out of your studies to do this. Oh. He contacted me. And so I appreciate that very much. Thank you for that. I've done a couple other like real science talks. And so I hope to continue with that. So this is one of many in the series. So again, thank you for that. Don't hang up after we do this outro here, but everybody, thank you for stopping by and watching, and we'll check you out. We'll see you all later.